let me ask a seemingly unrelated question at first, and then we'll come back to this circuit in just a second. Here's something we haven't talked about in a while, but we did a demo on it. If you have a current running through the presence of a magnetic field, and once again, this magnetic field is not due to the wire, it's due to something else, and we're just running a current through this externally applied magnetic field. We saw that there's a force on the wire. What direction is the force on the wire in this case? Okay, so we have, most of us, just barely, remember this, we have a current in the presence of a magnetic force, and you can just, well, first of all, you get the direction. We can just think of this as mobile charges moving, okay? If they were positive charges or negative, doesn't matter. If you have conventional current, think about the flow of positive charge. Positive charge is moving to the right, cross with a B into the page, thumb points up, right? So we have a positive y direction. And this, and you could do negative charges as well, but this comes from, remember we had also worked out another version of the magnetic force, which was I delta L cross B. Look familiar? Yes? No? Sort of? Okay. So there are magnetic forces on moving charges, and therefore there's magnetic forces on currents in a wire. Well, we've got a current in this circuit now. We said the conventional current was clockwise. Is there a magnetic force on the entire bar as a current runs through this bar, and it's drawn here, moving down through the bar? If so, what's the direction? Okay, this is always a question that causes some problems, although most of us are saying that there's got to be, or not just barely, actually a little less than a majority of us are saying that there's got to be a force to the left, okay, because that is the force that's essentially due to the current, okay. We've already established that there is a current, conventional current flowing clockwise, and so if you just look at the motion of the current, let's redraw this just to make the diagram a bit more clear. There's a current in this bar going down, and it's in the presence of a magnetic field everywhere in this region that is pointing out. And so, just from I, again, I delta L cross B, that's I, that's B, we get a force that is I cross B, thumb points in that direction. Now, didn't we just say that the magnetic force is upward on these charges? A lot of people answered that. Well, you got to be a little bit careful, okay? It's sort of thinking about the choice of system and what happens initially and then what happens once you have a current flowing. You think about initially the charges aren't moving, then you just start to move this bar, and if you're focusing on a single charge, there's going to be a force upward. But if you're focusing on the overall bar and looking at the current through it, then we're focusing on the force on that current and looking at this version of the magnetic force law to get the direction of the magnetic force. Now you can think of this another way, and this might help clear it up a little bit, which is this. Let me draw this bar again. The bar is moving this way, okay? And there are mobile charges in here, presumably electrons, that are moving upward, but the whole bar is also moving that way. So if I were to sort of look at a single electron, how's it really moving? Yeah, kind of up at an angle, right? If I were to sort of, if I could follow an electron as the bar moves to the right, an electron moves up. So the path the electron takes is sort of like that. Okay? If you think about that, then the force on that electron, V cross B is that way, but it's really an electron, so it's going to be, the force is going to be that way. You get a force that is, like any other QV cross B force, perpendicular to the velocity. But what we're doing is we're sort of looking at two different components of that force. Okay? I could break this force up into a component along the direction of the bar. That's the force that's causing the current to flow. Okay? And then I could break this force up into another component that's perpendicular to this bar. That's essentially this force. Okay? That's this force. And so we're sort of looking at two different aspects of the same interaction or same phenomenon here. It's just that we're focusing on two different things. One is what's causing the current to be driven in the first place, what's causing the polarization of the bar. And the other is once you have the current flowing, what's going to happen to the bar. Okay? And what is going to happen to the bar? It's moving to the right, but there's a force to the left, so what's going to happen? It'll slow down and come to a stop, won't it? Something. Does that make sense?